Everyone, on today's video, we want to go through an article. The title of this article is On Poroelastic Biot Coefficient for a Granitic Rock. The sample was taken from Lac du Bonnet bathyloid in the Canadian Shield. The biot coefficient itself is a parameter that we find in the theory of classical poroelasticity, where we deal with the mechanics of a fluid-saturated porous medium with elastic grains and an elastic skeletal structure. So in total, the coefficient plays an important role in how the externally applied stresses are distributed between the pore fluid and a porous skeleton. One of the most convenient ways for estimating the biot coefficient relies on a mechanical testing of the poroelastic solid. It can be either in a completely dry form or in a fully saturated state. But before I jump into the details of this article, I want to give you an introduction about the whole purpose of it. As you know, the management of heat-emitting and long-lived nuclear fuel waste is one of the most important topics nowadays to many industrial countries like Belgium, Canada, China, France, many. And as you know, they accumulated enormous spent fuel over several decades of nuclear energy production. Currently, the used fuel is stored at or near the reactor sites, but as you know, one of the problems is that as the reactors themselves age, they make many environmental concerns, and also they become unsuitable options for even temporary storage of heat-emitting waste because of the maintenance and monitoring issues that it requires over long periods. So many countries try to adopt a new way. It's called disposal schemes. What they do is that they take advantage of stable geological formations. These include like clay deposits, which they normally are used in Belgium, or argillaceous shales, and also opalynous clay, a kind of clay. And the topic that we want to talk about here, granitic rocks also, which they are probably used in Canada, China, and Japan. From a typical geological setting in a Lac du Bonnet, they saw that the granitic rock formation actually contains a sparse fracturing, and when they wanted to create a large underground opening in a highly stressed formation, they actually expected to see an excavitation damage zones, which we show it with EDZ. This EDZ can alter and change the thermo-hydromechanical processes after creation of a deep ground repository, and even after we place the heat-emitting fuel waste. In parts that are far away from excavitation, the rock formation are expected to remain intact, except for the presence of any sparse fracturing. In THM behavior, as you can see in a picture in geomechanics, what we're actually doing is that in a fluid-saturated porous medium, we want to see how the change in the temperature or flow or many other parameters, how will affect the geomechanic parameters in a porous medium. That's what we were doing, and I'm gonna give you more information about it when we move back to the biot coefficient. So what I was saying is that in the remote regions, the rock mass, as we said, is expected to be largely intact. So the THM behavior, we can describe it using the theory of thermoporoelasticity. The classical theory of thermoporoelasticity is an extension of the classical theory of poroelasticity, which was developed by biot. He did many extensive studies in this area, and he gave us many useful ways to a wide class of problems in geomechanics and geoscience. One of these actually includes the geological disposal of heat-emitting nuclear waste that we're going to talk about it in this video. What actually happens in fluid-saturated porous medium is that the externally applied stresses are partitioned between the stresses carried by the pore skeleton and the stresses carried by the pore fluid. In the classical theories of soil mechanics, the externally applied stresses are entirely borne by the pore fluid at the time that we're actually giving that sample the stresses. This assumption actually does not talk about the elementary concept of load partitioning though, but it actually respects the deformability of both the porous skeleton and the skeletal material. turn can change the fluid characteristics that are really important to maintain the integrity of waste disposal facilities. So in this sense, the classical theory of poroelasticity can be adopted as a representation of the cooled hydromechanical behavior of intact rock, which we can see in the nuclear waste disposal processes.